Hello, welcome back to A Slice of Physics. We are now ready to discuss capacitance and charge separation between the plates of a capacitor. We will first see how capacitance is related to the charge separation and the potential difference between the plates of a capacitor. And then we will tackle an important question. Even though there is a relationship between capacitance and these two other properties, we will see if capacitance depends on these two properties. So in other words, does capacitance of a capacitor change when the charge separation or the potential difference across its plates are changed? So let's again begin with an example of a parallel plate capacitor. So here's my parallel plate capacitor, and let's say I connect it for charging purposes to a battery that's got a potential difference of 12 volts, so delta VB is 12 volts, with the positive end at the bottom, and I let this battery take its time to charge the capacitor, and when it's done, it's got charges that are separated between these plates, positive at the bottom plate, negative at the top plate. And the battery can rest after the potential difference across the plates of the capacitor also becomes 12 volts. That's when equilibrium is reached and the capacitor is fully charged. So let's say the charge on this negative plate is minus Q and the charge on the positive plate is plus Q. And now the question is, how much charge do I need to separate in order to get that potential difference? Well, that's where capacitance comes in. We got an equation that relates the charge separation required to achieve a potential difference that says the charge separation equals the capacitance times the potential difference across the plates of the capacitor. So you can see that higher the capacitance of the capacitor, I would need to separate more charge in order to achieve the same potential difference. First, let's quickly see that the units work out in this case. If I go with the right hand side, the unit of capacitance is farad, which is coulomb over volt, and the unit of potential difference is just volt, and so the volt will cancel volt. I'll end up with coulomb, which is the unit of charge, so everything works out with this equation. Now let's take a couple of examples. Let's say I have a capacitor here that's got a capacitance of 2 microfarad. Now you'll remember from the previous video, let me just quickly review, that capacitance comes from the physical properties of the capacitor. So we had the equation that said capacitance equals kappa epsilon naught A over D, where kappa was the dielectric constant of the material between the plates, epsilon naught was the universal constant related to Coulomb constant, A was the area of the plates, and D was the distance between the plates. So once I have set all of that, I have a capacitance of the capacitor that's defined. And let's say in this case that was 2 microfarads. If I connect this capacitor to a 12 volt battery, I can now determine using the new equation how much charge needs to be separated. So using my equation over here, I can say Q1 for this capacitor equals C1 times delta VC, and delta VC will get to 12 volts when it's fully charged. So this will become 2 microfarad times 12 volt. And so this is 2 times 10 to the negative 6 farad times 12 volt. And that ends up being 24 times 10 to the negative 6 farad times volt. And because farad is simply coulomb over volt, this farad times volt is coulomb. So this gives me 24 microcoulomb. And to take a different example, if I had another capacitor over here that had a capacitance of 1 microfarad, and I connected it to the exact same 12 volt battery and let it fully charge this capacitor, how much charge would need to be separated? So in this case, using that same equation, I would get Q2 equals C2 times delta VC, and when the capacitor is fully charged, the potential difference for the capacitor would be 12 volts, same as the battery's value. So now I have 1 times 10 to the negative 6 farad times 12 volt, which gives me 12 microcoulomb. So in both these cases, the potential difference across the plates of the capacitor reached 12 volts. because they were both charged fully by a 12-volt battery. But in one case, I needed 24 microcoulomb. Let me show that notationally like this. Whereas in the other case, I only needed a charge separation of 12 microcoulomb. So less charge separation to get the same potential difference. And that's because the capacitance of these two capacitors were different. Capacitance is what controls how much charge I need to separate in order to achieve a given potential difference. So when I build capacitors, if I want a bigger flash of light for a camera flash, I want to build a higher capacitance capacitor, because when I use a battery, it'll have to move more charge to achieve that potential difference. And when I connect this capacitance to a bulb, there'll be more charge flowing through that bulb, giving me a bigger pop. Okay, there's one other important thing I want to cover with you, and I'm going to move things around and create some room so I can do that. Okay, I'll summarize the two equations relating to capacitance over here. The first one told us how capacitance depended on the physical properties of the capacitor, and the second one is a rearrangement of the equation we just discussed, which tells us how capacitance is related to the charge and the potential difference across the plates of the capacitor. So the example I want to take now is one of these capacitors. Let's say I take this first one, which had a 2 microfarad capacitance, and somehow, and for right now let's not worry about how, I double the charge separation on its plate. So rather than have the 24 microcoulomb separation, I'm now going to have a 48 microcoulomb separation. So there we go. The question now is, what happens to the capacitance of this capacitor? So the Q now, rather than being 24 microcoulomb, which it was in the example at the bottom here, I change it to 48 microcoulomb. I separate more charge between the plates somehow. What happens to the capacitance? Well, you might be tempted to look at this equation that connects C and Q and conclude that if Q doubles, C has to double. Well, it turns out that that is not the case. It does not work like that, because you got to remember that the other equation is also valid. Both of these equations have to work all the time. So the first equation told us that the capacitance depended on the area of the plates, the distance between the plates, and the dielectric constant of the material between the plates. I took the same capacitor from here and separated more charge. By doing so, I did not change the area of the plates, I didn't change the distance between the plates, nor did I change the dielectric constant of the material between the plates. So its capacitance cannot change. It has to remain the same as what it was. So the first equation tells me that the capacitance is still 2 microfarad. And so now we can look at this equation and say, if capacitance does not change and Q doubles, how can I do that? Well, I can do that if I also double delta VC as I double Q. And that, in fact, is what would happen in this case. For a charge of 48 microcoulomb having a capacitance of 2 microfarad, I would have to change delta VC. So I can use this equation at the bottom here and set up 48 microcoulomb equals 2 microfarad times delta VC, the new potential difference. And rearranging these, I would get delta VC equals 48 microcoulomb divided by 2 microfarad, which is 48 times 10 to the negative 6 coulomb divided by 2 times 10 to the negative 6 farad. The negative 6 cancels each other. 2 goes into 48 24 times. So I would get 24, and coulomb over farad is simply volt. So I'll get a potential difference of 24 volts. So by moving more charges, I created a bigger potential difference between these plates. And in fact, the way to accomplish this, the way to achieve a higher charge separation between the plates, would have been to connect this to a different battery. I've now gotten it connected to a bigger battery that's capable of a higher potential difference. So the potential difference of this battery here is 24 volts, and when it fully charges this capacitor, it'll have to move more charges than the previous battery did in order to get potential difference between the plates to increase from 12 volts to 24 volts. So the best way I can suggest that you work with this is to remember the difference between these two equations. The first equation, think of it as the equation of how the capacitor is built. That's what determines the area of the plates, the distance between the plates, and the material between the plates. And once I build a capacitor, I fix its capacitance. So the capacitance depends on how the capacitor is built. And think of this second equation as how the capacitor is used. That's when I determine how much charge I put on the plates. That's when I determine what the potential difference between the plates is. So that's a usage of the capacitor. And the capacitance of the capacitor, even though it's related to the charge separation and the potential difference, it does not depend on these factors. Now, since this is a little bit of a tricky point, let me just give you an analogy that might help you. You've seen the equation F equals ma, force equals mass times acceleration. Well, if I take the same object and apply twice the force on it, what happens to its mass? I can rearrange this equation to say mass equals force divided by acceleration. If I double the force, this equation might make it look like the mass might double, but you know it doesn't. The mass of an object is dependent on how much stuff it's made of, and that doesn't change, simply dependent on how much force I apply on it. So if I double the force, the acceleration also doubles so that the ratio remains the same and the mass does not change. Same thing here. If I double the charge separation, the potential difference across the plates also doubles. The capacitance doesn't change because that's only dependent on how it's built, not how it's used. In this slice of physics, we learned more about capacitance, specifically about how it affects the charge separation between the plates of a capacitor in order to achieve a known potential difference. We reminded ourselves that the capacitance of the capacitor is a property of the capacitor and only depends on how the capacitor is built and not on how it's used. So it depends on the area of the plates, the distance between the plates, and the dielectric constant of the material between the plates. And importantly, it does not depend on the charge separation between the plates or the potential difference between the plates. Even though we have a second relationship here for capacitance that tells you how those factors are related, that does not suggest a dependence. So this equation tells us that if I connect two different capacitors to identical batteries with the same potential difference, by the time the capacitors are fully charged, they would have different charges separated between the plates, and how much charge separation is required is determined by the capacitance of the capacitors. Higher the capacitance, more the charge separation for the same potential difference. Thanks, and I'll see you later.